Okay, so I'm going to try and record this lesson, and it's going to be a little different than how I usually do it because I'm having to use Google Slides instead of PowerPoint, so it may take me a little while to get used to what I'm doing, but I'm going to try to work with your note packet to keep you, make sure that I'm doing the same thing you are. So here's my general definition of work. I would pause and write this down. Its work is scalar in nature, which makes life much easier for you. You don't have to worry about magnitude and direction. But what you do need to concern yourself with is there must be a part of the force acting in the direction of the motion. So that's what that equation is telling you right there. Work must equal some part of the force acting in the direction of the motion. That amount of force times that displacement is going to give you the work done. But you have to have part of the force acting in the direction of the motion. So probably time to stop for a while, get that down. Now, if you look at this, and I'm going to try to go to an ink pen, we'll see how it goes. There we go. If you are shoving a box like that, and F is parallel to the ground, then the angle between your force and the displacement, if it moves that way, is 0. The cosine of 0 degrees is 1. So it's basically F times 1 times the amount of displacement. No big deal. If, however, I have a box and I pull it with a rope like that, then this is the work. The force that creates the work, because that's the part that's acting in the direction of the motion. If you think about this force, it's acting horizontally, but it's also pulling straight up. Well, to get the work done, you just want to take the component acting in the direction of the motion. If I'm moving it like that, and that's my theta, then this leg of the triangle will be F cosine theta. So there's my Fx, and I'm going to multiply it by my distance or my displacement in the direction of the motion. So make sure you get that filled in. I'm going to try to manipulate this technology. Alright, so that took it away. Alright, so let's move on. In order for work to be done, there must be 3 things that are necessary. There has to be a force applied. The force must act through a distance called the displacement, and the force must have a component along the displacement. So again, you need to pause and write those 3 things down. So ask the substitute to pause, and then you can get those 3 things written down. So if you look at these pictures here, I'm assuming you've got all this stuff written down. Here is a gentleman leaning against the big large crate. This man pushes and pushes and pushes with a force F, but no motion occurs, so no work is done right there. No work is done. Well, not cooperating. If I look at this one, the force is acting in the direction of the motion, so work is done. That's equal to FD. Here's the lawnmower. She's pushing along that hypotenuse. This is the part that's actually doing the work. So F cosine theta times D will help us figure out how much work she does. Okay? Alright. It says read the following statements and determine whether or not they represent examples of work. So a teacher applies a force to a wall and becomes exhausted. Force is applied, no movement occurs, so no work is done. So let me see if it'll let me write on this yet. Okay. Alright. Next statement is a book falls off a table and free falls to the ground. So gravity is doing work because there is a displacement in the direction of the force. Gravity is pulling it down, it's moving in that direction, so work is done. Alright, here's a gentleman carrying a sack of groceries, and it wants to know you're carrying groceries to the car. So here's your force, here's your distance, or your displacement, I should say. This force is not acting in the direction of this displacement, so no work is done. Displacement and the applied force are not in the same direction. And then slide 5 has a couple of options. A truck carries a box in its bed 100 meters. So there's no work done, because if you look at the force acting on the crate, it's upward. The displacement is straight ahead, so those are at right angles. Cosine of 90 is 0. No work is done. The units for work are force times distance. Alright, I don't see, it looks like on your slideshow there, or on your note packet, it says if you push an object twice as far while applying the same force, you do twice as much work because the distance doubles, so the amount of work has to double. The next one says if you push an object just as far while applying twice the force, you're going to still do twice the work, because if this thing would cooperate, W is equal to FD. So in the first example, we did twice as much distance, so we did twice as much work. The other example, we doubled the force, kept the distance the same, so we still did twice the work. So that should help you fill in those. Okay. Alright, let's move on. Let me see what's going to happen now. Have no idea what's going on with this craziness here. Alright. So the units of work are newtons times meters, which is an Nm. Sometimes you'll see it as an N-M. And a newton meter is also called a joule. Joule. Also called a joule. Okay? Alright. In English system, we call it foot-pounds. You're never going to have to know that. I will never give you a foot-pound question. Okay. So let's look at this one. It says if you push an object, that's the ones that we just already did. Way to go, Miss Walker. Okay. So we've already worked through those. Okay, positive work occurs when you apply a force in the same direction as the motion, because the angle between F to the right, D to the right, the angle theta is 0 degrees. So if work equals F cosine theta D, that's going to be 1. Oops, way to mess it up. That's going to be 1, so I have positive work. Okay, so take some time and fill that out. Now let's go on to the next one. So the work done is 160 newton meters, or 160 joules. Okay, now look at this. My force is to the left, my displacement is to the right. The angle between those two is 180 degrees. The cosine of 180 degrees is a -1. So if friction is to the left, you can call it a -10, or you can just realize that the angle between the force and the displacement is 180, and that would give you a negative also. Okay? And it makes sense if you think about it, because the work done by friction takes energy away, so there's a negative sign in front of it to show you a loss of energy. So the work in this case is -40 joules. And again, you can pause and get this in your notes. Now sometimes we do work by applying a force at an angle. So if you look at that picture, this is the only part of the force that's doing any work. So I'm going to take my hypotenuse of 70 newtons, multiply it by the cosine of that angle between the parallel and the applied. That's a 60-degree angle, and you get 12 meters for the displacement, so you find out you do 420 joules of work. It's positive work. You're increasing the energy of the object. So again, you can stop it if you need to. So there's our work. Alright, this one says what work is done by a 60 Newton force in dragging the bag a distance of 50 meters when the force transmitted by a handle making an angle of 30 degrees with the horizontal. So let's see if it works it out. So there's our formula. W equals F cosine theta D. F is 60 newtons from right here. Cosine theta, that's a 30-degree angle. And D is 50 meters. So 60 times 50 is 3,000, and then you're going to multiply that by 0.866 because that's the cosine of 30. And there's your work. It's positive because you're applying the force in the direction of the motion. Again, you can stop the slideshow and write this all down. All right, example 2. This time we're going to shove 200 newtons down that way. We're going to move in this direction. So this is the force that's doing the work. So F cosine theta times the displacement, x or d, whatever you want to call it. The hypotenuse is 20. The angle between the displacement and the supplied force, the part that's acting in the direction of motion, is a cosine of 30 times 20 meters. That's my displacement. So there's my work is equal to 3,460 joules. Work is going to be called positive because Fx and x, the displacement, are in the same direction. If you're looking at a graph of force and displacement, the area under the curve, even though this isn't a curve, we're going to use that term generically, the area under the curve is going to tell you how much work is done, because if you look at it, the force is constant. The change in displacement is x2 minus x1, so if this were 15 meters and this would 5 meters, you would say I displaced it 10 meters. So the work done is equal to F times delta x, the change in the position. And I don't see a place for this on your notes, but you can make a place somewhere. So the work would be 40 newtons times 3 meters, or 120 joules of work would be done. Power is how quickly we do the work. So power is just work over time. So I wind up with joules per second. Joules per second is also called a watt, W-A-T-T. In the English system we call it horsepower. There's a conversion between horsepower and watts. There it is, 746 watts is equal to 1 horsepower. So pause the slide and get that in. I believe that we have an example problem. A 0.25 horsepower motor is used to lift the load at the rate of 5 centimeters per second. How great a load can it lift at this constant speed? Well, here's a new equation. Power is force times velocity. And I'll try to show you where that came from. Let's see if it's going to, yeah, there we go. Alright, so power is work over time. Work is force times distance. Distance over time is the same thing as velocity. So that's where that came from. So I figured out my force, and then I converted my force into a mass because that's what they wanted to know. Okay, they give you a quarter horsepower. Make sure you change it into watts. And also realize that this is in centimeters per second, so it has to be converted into meters per second right there. So that's watts, and that's meters per second. And a watt is a joule per second. A meter per second is velocity. Those will cancel. So a newton meter over meter gives me the unit for force, which is newtons. Okay? So pause if you need to. All right. All right, so we're going to stop right there. I want you to work on problems 1 through 6. Oops, way to go, Miss Walker. So you have some time in class to work on problems 1 through 6. Tuesday we'll work on energy some more. Monday there will be a catapult launching. And I believe we're going to do a review kind of fast check on Tuesday. That'll be a daily grade. And I'll talk to you more about that on Monday, so don't flip out. It'll be all right. See you Monday, guys.